Welcome to this presentation on NP-complete and NP-hard problems, which are fundamental concepts in the study of algorithms. To begin, let's understand what NP-complete and NP-hard mean. These terms describe certain classes of problems that are crucial in the field of computer science, specifically in the design and analysis of algorithms. Now, let's take a closer look at NP-complete problems. NP-complete problems are the hardest problems within the NP class. These problems satisfy two key conditions. The problem is in NP, meaning that solutions can be verified quickly in polynomial time. The problem is also NP-hard, meaning that any NP problem can be reduced to it in polynomial time. The key idea behind NP-complete problems is that they are verifiable quickly, but they are not necessarily solvable quickly. In other words, while we can easily check whether a given solution is correct, finding the solution may take a lot of time, especially as the problem size increases. But why do we study NP-complete problems? Studying NP-complete problems helps us understand the limits of efficient computation. When we identify a problem as NP-complete, it tells us that finding a polynomial-time solution is very unlikely. This is because no known algorithm can solve NP-complete problems quickly in all cases. Instead, knowing a problem is NP-complete helps us think about alternative strategies, like using heuristics, approximations, or looking for special cases that might allow for easier solutions. Let us now look at some common examples of NP-complete problems. The first example is Boolean satisfiability, also known as SAT. In this problem, we check whether there exists an assignment of true or false values to variables that makes a Boolean formula true. SAT was the first problem proven to be NP-complete. The second example is the Clique decision problem. Here, the goal is to determine whether a graph contains a clique of a given size, meaning a set of vertices where every vertex is connected to every other vertex. Next is the vertex cover problem. This problem asks whether it is possible to select a limited number of vertices such that every edge in the graph is connected to at least one selected vertex. Another important example is the Hamiltonian cycle problem. This problem checks whether a graph contains a cycle that visits every vertex exactly once and returns to the starting vertex. We also have the subset sum problem. In this problem, we determine whether there exists a subset of given numbers whose sum equals a specific target value. Finally, the Traveling Salesman problem, in its decision version, asks whether there exists a tour that visits every city exactly once and has a total cost less than or equal to a given value. All of these problems are NP-complete, meaning their solutions can be verified quickly, but finding the solution efficiently is considered computationally difficult. Example: step-by-step explanation of Hamiltonian cycle. Step 1. Given an undirected graph G, V, E with n vertices, determine whether there exists a Hamiltonian cycle in the graph. We begin the Hamiltonian cycle by selecting vertex 1 as the starting point. The path currently contains only the starting vertex. Let me know if you need more details or adjustments to the script. Give detailed TTS script. Here's a more detailed text-to-speech (TTS) script based on the image. Example: step-by-step explanation of Hamiltonian cycle. Step 1. In this step, we are given an undirected graph represented by G, V, E, where V denotes the set of vertices and E represents the set of edges. The graph contains n vertices. Our task is to determine whether there exists a Hamiltonian cycle in the graph. A Hamiltonian cycle is a cycle that visits every vertex exactly once and returns to the starting vertex. The graph in the image shows 4 vertices labeled A, B, C, and D, with edges connecting them. Let's analyze it to check if a Hamiltonian cycle exists. We begin the Hamiltonian cycle process by selecting vertex A, denoted as vertex 1, as the starting point. In this step, the path currently contains only the starting vertex A. This is shown by the green coloring of vertex A in the diagram. The visited path is initially shown as 1, 1, 1, 1, 1, 1, 1, 1, indicating that vertex A is the starting point and has been visited, while the other vertices B, C, and D have not been visited yet. Step 2. Now we move to the second step of finding the Hamiltonian cycle. Vertex 2, labeled as B, is adjacent to vertex 1, labeled as A. Since vertex B has not been visited yet, and there is a direct edge between A and B, it is a valid choice. Therefore, vertex B is added to the path. Both vertices A and B are now marked as visited, which is shown by the green color in the diagram. The direction of movement from A to B is indicated by the arrow. At this stage, the visited path is represented as 1, 2, minus 1, minus 1, which means vertices 1 and 2 have been visited, while the remaining vertices are still unvisited. Step 3. Next, we consider vertex 3, labeled as C. Vertex C is directly connected to vertex B, and it has not already been included in the path. Since vertex C is adjacent to the previously visited vertex and has not been visited before, it is a safe and valid choice to continue the Hamiltonian path. Thus, vertex C is added to the path. Vertices A, B, and C are now marked as visited, as shown in green. The arrow indicates movement from vertex B down to vertex C. At this point, the visited path becomes 1, 2, 3, minus 1, indicating that 3 vertices have been successfully included in the path, with only one vertex remaining to be visited. Step 4. In this step, we consider vertex 4, labeled as D. Vertex D is directly connected to vertex 3, labeled as C, and it has not yet been included in the path. Since vertex D is adjacent to the previously visited vertex and is not already present in the path, it is a safe and valid choice according to the rules of a Hamiltonian path. Therefore, vertex D is added to the path. Now, all 4 vertices A, B, C, and D are marked as visited, which is shown by the green color in the diagram. At this stage, the visited path becomes 1, 2, 3, 4, indicating that every vertex in the graph has been visited exactly once. Step 5. Finally, we check whether the last visited vertex, vertex 4, is connected back to the starting vertex, vertex 1. From the diagram, we can see that vertex D is directly connected to vertex A. This connection allows us to return to the starting point and complete the cycle. As a result, the path 1, 2, 3, 4, 1 forms a closed loop that visits every vertex exactly once. Hence, this path is a valid Hamiltonian cycle for the given graph. IME complexity. The time complexity of this problem is O of n factorial, written as O n. This indicates that the problem becomes extremely expensive to solve as the input size increases. The problem belongs to the NP-complete class, meaning there is no known polynomial time solution and it is considered computationally hard. Applications: circuit design and verification. SAT problems are used to verify the correctness of logical circuits. Network analysis. Problems like Clique and Vertex cover are applied in social networks and computer networks. Scheduling problems. These problems help in job scheduling and efficient resource allocation. Cryptography. Hard combinatorial problems are used to design secure cryptographic algorithms. NP-hard, also known as NPH. What is NP-hard? NP-hard problems are at least as hard as NP-complete problems. They may not belong to NP, which means their solutions may not be verifiable in polynomial time. NP-hard problems can include decision problems, optimization problems, or even undecidable problems. The key idea is that NP-hard is a broader class that contains all NP-complete problems and even harder ones. Why do we use NP-hard? NP-hard helps us understand the difficulty of optimization and computationally intensive problems. It also helps identify problems where exact solutions are impractical, encouraging the use of approximation algorithms or heuristic methods. Examples. Some common examples of NP-hard problems include the Traveling Salesman problem in its optimization version, the knapsack problem in its optimization version, the halting problem, which is an undecidable problem, and job shop scheduling in its optimization version. Example: step-by-step procedure for the job sequencing problem. Problem definition. We are given n jobs, and the goal is to schedule the jobs to maximize profit. Each job has a deadline, denoted as D sub I, which means the job must be completed by this time. Each job also has a profit, denoted as P sub I, which is earned only if the job is completed before its deadline. Each job takes 1 unit of time, and only one job can be processed at a time. Step 1. We are given 3 jobs with their deadlines and profits. Job J1 has a deadline of 2 and a profit of 50. Job J2 has a deadline of 1 and a profit of 10. Job J3 has a deadline of 2 and a profit of 20. Step 2. We sort the jobs based on profit in decreasing order. After sorting, the job sequence becomes J1 with profit 50, followed by J3 with profit 20, and then J2 with profit 10. Step 3. We initialize the time slots. The maximum deadline among all jobs is 2. So, we create 2 time slots. Initially, both time slots are empty and represented as dash dash. Step 4. Schedule the jobs. First, consider job J1. Job J1 has a profit of 50 and a deadline of 2. We look for the latest empty time slot less than or equal to 2. Slot 2 is free, so job J1 is assigned to slot 2. The current slots are empty, J1. Next, consider job J3. Job J3 has a profit of 20 and a deadline of 2. We again look for the latest empty slot less than or equal to 2. Slot 2 is already filled, but slot 1 is free. So, job J3 is assigned to slot 1. The current slots are J3, J1. Now, consider job J2. Job J2 has a profit of 10 and a deadline of 1. We check the latest empty slot less than or equal to 1. Slot 1 is already filled, so job J2 cannot be scheduled and is skipped. Step 5. Calculate the total profit. The scheduled jobs are J1 and J3. The total profit is 50 plus 20, which equals 70. Step 6. Final job sequence. In the final scheduling result, time slot 1 is assigned to job J3 and time slot 2 is assigned to job J1. This gives us the final sequence of jobs. Now, let us look at the complexity of this approach. The time complexity is O of n factorial, which means the algorithm becomes very slow as the number of jobs increases. Because of this high complexity, the problem belongs to the NP-hard class. Now, let us discuss some applications of NP-hard problems. In operations research, these problems appear in optimization tasks such as the traveling salesman problem and scheduling. In industrial planning, they are used for resource allocation, logistics management, and supply chain optimization. In artificial intelligence, NP-hard problems arise in hard search problems, planning, and constraint satisfaction. Finally, in cryptography, NP-hard problems form the basis of secure algorithms by relying on computationally hard problems. This concludes the explanation of the final job sequence and its applications. Relationship between NP-complete and NP-hard problems. In the diagram, you can see two categories, NP-complete and NP-hard. NP-complete problems are a subset of NP-hard problems. This means that all NP-complete problems are also NP-hard. However, not all NP-hard problems are NP-complete. Some NP-hard problems may not be in NP, which means they can't be solved in polynomial time. This diagram helps illustrate that while NP-complete problems are a special kind of NP-hard problem, NP-hard problems are more general and can include problems that don't necessarily belong to NP. That's the basic idea behind the relationship between NP-complete and NP-hard. Thank you for your attention.